Your phone joins a 5G network in seconds. But before it can send a single byte of your data, the network has to answer one hard question. Is this device really who it claims to be? Think of a high security office building. You cannot just walk in because you look confident. You present an ID, the system checks a central database, and only then does a guard unlock the door. 5G registration works the same way, except the building is a nationwide radio network, and a forged ID could mean stolen service, eavesdropping, or a fake base station tricking your phone. Authentication is the handshake that proves mutual trust between your user equipment, the UE, meaning your phone or modem, and the operator's core network. Get it right, and you enter a registered state ready for sessions. Get it wrong, and the door stays shut. In this lecture, we walk the full path of a 5G registration attempt, then zoom into a failure case. The UE returns a wrong response value, the core detects the mismatch, and the device is pushed back to deregistered. By the end, you will see exactly which network functions talk, what messages carry, and why one bad RES star is enough to kill the whole attempt. Before any message flies, meet the cast. 5 roles show up again and again. First, the UE, user equipment. That is the device trying to get on the network. It holds secret credentials provisioned by the operator, but it never ships the permanent identity in the clear. It sends a concealed form instead. Second, the AMF, Access and Mobility Management Function. Picture the front desk of the building. Every registration and mobility event hits the AMF first. It does not own the master secrets, but it orchestrates the conversation and makes the final admit or reject call toward the UE. Third, the AUSF, Authentication Server Function. This is the specialist security office. It sits between the AMF and the home subscriber database, runs the authentication procedure, and derives the values the AMF will later check. Fourth and fifth travel as a pair, the UDM, Unified Data Management, and the ARPF, Authentication Credential Repository and Processing Function. Together, they are the vault. The ARPF holds long-term keys and builds a fresh 5G home environment authentication vector, shortened to 5G HEAV. The UDM packages that vector and answers authentication GET requests. Remember the chain of trust. UE talks to AMF over the radio. AMF talks to AUSF. AUSF talks to UDM and ARPF. Secrets stay deep in the vault. Challenge material moves outward. Proofs move back in. The journey starts when the UE sends a registration request. In the building analogy, this is you walking up to the front desk with a badge holder and a list of floors you need. 4 pieces of content matter for our story. Registration type tells the network what kind of attach this is: initial registration, mobility update, or periodic update. Think of it as saying whether you are a first-time visitor or renewing an existing pass. SUCI, the Subscription Concealed Identifier, is how the UE names itself without exposing the permanent subscription permanent identifier on the air. Encryption protects privacy against passive sniffers on the radio link. Security capabilities advertise which algorithms and features the UE supports, so the network can pick a common suite. Requested NSA-AI is the network slice selection assistance information. It is the UE asking for particular slices, for example, enhanced mobile broadband versus ultra-reliable low latency. The floors of the building it wants access to. None of this yet proves the UE knows the long-term secret. The request is a claim plus a wish list. Proof comes later in the authentication dance. But without a well-formed registration request, the AMF has nothing to start. Once the AMF has a registration request that needs authentication, it reaches toward the home network. The path runs through the AUSF into the UDM, which asks the ARPF to mint fresh authentication material. That material is the 5G home environment authentication vector, 5G HEAV. Do not treat the name as decoration. Home environment means it is built from the home operator's long-term key material. Authentication vector means a one-time bundle of challenge data and expected answers, not the long-term key itself. Here is the intuition. The vault never ships the master key to the front desk. Instead, it rolls a random challenge, runs the same cryptographic functions the legitimate UE will run, and packages what to send the UE and what correct answers should look like after hashing. That package is the vector. The UDM returns it on the NDM authentication GET response toward the AAUS. At this moment, the AAUS holds home grade proof material. The UE has not been challenged yet. The AMF has not seen the expected hash it will later compare. The vault did its job: create a single-use exam that only a UE with the right secret can pass. The AUSF now transforms the home vector into something the AMF can use without learning every home secret. A critical derived value appears here, HXRES star. Read that as the expected hash of the expected response. The AUSF computes it from the material in the 5G HEAV, so the serving AMF can later run a local check. The AMF does not need the full home key hierarchy. It needs a compact expected fingerprint. On the service interface, this rides NOSF UE authentication authenticate messaging. In plain language, the AMF asked the AUSF to authenticate this subscriber. The AUSF answers with an authentication challenge package plus the HXRES star. The AMF should hold on to. Gatekeeper analogy. The Central Security Lab verified the badge stock and printed a one-time code sheet. It hands the front desk a sealed envelope of what to ask the visitor, and a separate note of what the correct hashed answer must look like. The front desk can catch a wrong code without calling the lab for every digit. When this step finishes, the AMF is armed. It still has not challenged the UE. That is next. Now the radio side wakes up. The AMF sends an authentication request down to the UE. This message is the security office sliding a challenge card across the counter. Here's a fresh problem only someone with the real subscription credentials can solve. The UE receives RAND-like challenge material and related parameters carried in that authentication request. It does not receive the network's expected RES star. That stays on the network side. Why challenge response instead of sending a password? Because the air interface is hostile. A password repeated becomes stealable. A one-time challenge binds proof to this exact attempt. Even if an attacker records the exchange, they cannot replay it later as a fresh registration without the long-term key. From the UE's point of view, the job is mechanical and strict. Take the challenge, combine it with the provisioned secret using the standardized 5G algorithms, and produce RES star, the response star value. Produce related keys for later confidentiality and integrity if authentication succeeds. For our failure story, RES star is the star of the show. The network is waiting. The next message from the UE decides admit or reject. The UE runs its local crypto. Using the challenge from the authentication request and its own key material, it calculates RES star. It then sends an authentication response carrying that RES star back toward the AMF. In a clean run, RES star matches what the home network predicted when it built the vector. The serving side will hash and compare. Match means the UE proved possession of the credential without ever transmitting the credential. Hold the building picture again. The visitor was given a sealed puzzle derived from a master pattern only real badge holders share. They solve it at the counter and hand back the answer sheet. They do not hand over the master pattern. Two paths fork from here. Path 1, honest UE, correct RES star, leads to successful authentication, security mode setup, and eventually a registered mobility state. Path 2, wrong RES star, whether by bug, tampering, or deliberate manipulation in a test scenario, leads to detection at the AMF and a hard reject. Our source focuses on path 2. So from this point, we treat the authentication response as carrying an incorrect RES value. Everything after is how the network notices and how rejection propagates. Before we break the attempt, lock in the success baseline so the failure is meaningful. On success, the UE's res star, after the same hashing the network expects, lines up with HXRES star held by the AMF. The AMF informs the AUSF that authentication succeeded. Anchor keys and session keys can be derived consistently on both sides. The AMF can proceed with NAS security mode command, complete registration accept, and move the UE into a registered state where ordinary mobility and session management make sense. Notice what success really certified. Not that the UE is a nice device, not that the user paid the bill yesterday. It certified that this UE right now could solve a home network issued puzzle that only the legitimate subscription secret unlocks. Billing, policy, and slice admission can build on that root of trust. If you only memorize reject causes, you miss why the accept path is safe. The comparison at the AMF is the hinge. Same hinge, opposite swing gives failure. Here is the failure scenario the source highlights. The UE sends an authentication response, but the res star inside is incorrect. Call it message manipulation. The value on the wire is not the honest output of the UE's credential and the challenge. In a lab, you might flip bits to test negative paths. In the wild, causes range from implementation bugs to an attacker trying to fake a response without the real key. The network's job is identical in every case. Do not trust the UE's word. Check the math. Analogy, the visitor slides back a code sheet, but 3 digits are wrong. Maybe they misread the puzzle, maybe they are bluffing. The guard does not argue about motives. The guard checks the sheet against the expected fingerprint from the security lab. Important precision. The AMF does not necessarily rerun the entire home ARPF function. It uses the HXRES star it already received from the AUSF, and it derives HRES star from the res star the UE just sent. Those two hashes are what collide or clash. So the crime scene is small. One response field, two hash values, one comparison. This is the part that matters. The AMF calculates HRES star from the received RES star, then compares it to the stored HXRES star. If they are equal, authentication proof holds at the serving node. If they differ, the proof fails. Full stop. In our manipulated case, they differ. The mismatch is the detection event. Why hash at all? RES star itself may be larger or structured so that the serving AMF is handed a compact expected digest rather than every intermediate home value. The star naming marks 5G specific derivations in the authentication framework. You do not need the full 3GPP equation sheet to grasp the control logic. Expected digest versus digest of what UE sent. When mismatch hits, the AMF does not quietly retry forever and does not pretend success. It begins the reject path toward both the AUSF and the UE. Detection lives at the AMF comparison. That is the hinge we flagged earlier, swinging to deny. If you remember only one mechanism from this lecture, remember this comparison. Everything else is set up so that this check is possible without exposing long-term keys on the radio or at every serving node. With the mismatch flagged, signaling turns negative. The AMF sends an authentication rejection indication toward the AUSF. The AUSF, as the authentication server for this procedure, learns that the serving side did not accept the proof. It can update procedure state and respond so the AMF's view of the authentication attempt is consistently failed. Then the AMF sends authentication reject to the UE. On the air, that is the guard saying access denied. Leave the counter. The UE must not assume half-open security context from this attempt. Whatever temporary state it built while computing res star is discarded for registration purposes. Notice the order in the source story. Detection at AMF, inform AUSF, reject UE. The AUSF was the brain that armed the AMF with HXRES star. Closing the loop with the AUSF keeps the core consistent. The UE only needs the final reject. It never receives a tutorial about which hash failed. Security protocols stay tight-lipped on failure details that could help an attacker. From a testing angle, this is also where you validate that negative paths do not leak keys or leave the UE half-registered. Clean failure is a feature.